Okay, we're in section 9.4, and we're going to be looking at special diodes, and we'll be looking at this in two sections. There are many diodes that have special properties that are useful in electronic circuits. Now, up till now, we've just been looking at basic diodes, and we've been using them in rectifiers, clippers, power supplies, etc. A Zener diode is much like a standard diode in many respects, except that it is designed to operate in, notice here, the reverse breakdown region of its operating curve. Now, all the diodes we have been looking at up to this point, if we operate them in reverse voltage, they either look like an open circuit, or if you put too much voltage across them, you destroy the diode. But the Zener is designed to be operated in the reverse breakdown region. And you have a simulation. In fact, we'll be going to this simulation shortly, figure 09-31.MSM. Okay, basic Zener characteristics. Zener diodes are operated in their reverse breakdown mode to provide voltage regulation. Now notice voltage regulation in a circuit. Voltage regulation means that it's keeping a voltage at a very stable value. The point where the reverse current begins to increase is called the knee voltage, and that's going to be right here, the voltage, the knee voltage right here. The current at this point is the knee current, and you'll see this right here. And another value, we have IZM, and this is the maximum allowable current. Now, Zeners are designed for many different voltages and many different currents, and in this particular case, whatever this value is here, this is the voltage that this one is designed to operate at. Now, this is the circuit that we're going to look at in Electronics Workbench, and what we have is, here's an IN 4733. If you were to look that up, you would find that that is a 5-volt Zener. And so the idea here is that here we have a voltage that's coming in, and this voltage may be, this is going to be, obviously it's going to be above 5 volts. In fact, it must be above 5 volts for this to work. But the Zener will begin to conduct, and it's going to conduct in the reverse region, and it will conduct at 5 volts. And regardless of what this voltage is over here, it will stay at 5 volts, and it will make sure that a 5-volt value is delivered to the load over here. And then this is a screen save from the simulation. But what I want to do now is jump over to the simulation, and here is the simulation. And let's see, why don't we, here we have let's talk about what we're doing first. Here we have a voltage source, and this voltage source is set up to supply a triangular wave into this input. And that is going to be fed to the Zener. The Zener will keep a stable voltage in spite of the fact that the input is changing radically. Now, let's take a look at the inputs and outputs. Let's go turn on the oscilloscope here. And what we will see, in fact, let's run the simulation. And you'll see here we have the triangular wave coming in, and this blue line here is the output voltage. And if we go in here, you'll notice we have the oscilloscope set up. Channel A is set to look at what is the input value, and channel B is looking at what is the voltage across the Zener. And you'll see that the input is changing quite radically, and yet the voltage across the Zener is the blue line, which is very constant. And if we turn on the ohm meter here, the ohm meter is set across the load resistor in parallel with the Zener, and you see that it's at a very stable value right at about 5 volts. Now, why don't we, let's pause this, and let's take a closer look at our input. I'm going to scroll back to time 0 on the input, and let's just take a look at what are our input values. So here we have, let's see if we can separate out our 1 and 2, or 1 point here, so our 2 over the way over there. If we go here to our highest point here, we're going to see that we're about 11.5 volts. And then our blue line here is at about 5 volts. And just as a frame of reference, these 1 and 2, if we scroll this over all the way over here, you'll see we're looking at time 1 and time 2, and they're both showing the 11.5 and the 5. This is showing that in relation to time, this started at 0, and so if we brought, let's grab 2 and bring it over to here, and bring this one over here. And so what you'll see here is that the time, we're looking at the time between T1 and T2 is 3 milliseconds. The voltage at T2 is 5.6 volts, and the blue is 5. So what becomes off, and the variance, the difference between T2 and T1 is 5.9 volts. So it's going from 11.5 volts down to 5.6 volts, and it's changing constantly. And yet our output is very constant. And this is the purpose of a Zener diode, is for voltage regulation. Earlier we had talked about computer circuits that needed a stable DC voltage, and Zener regulators are commonly used in that application. And remember that the computer needed to have 5 volts, and so this could, when the AC comes in, the AC is going to have ripple in it, and it can vary from the wall. The Zener here is capable of stabilizing that value, and you can see quite clearly that here we have a input that is changing quite radically, and yet the Zener is able to keep that voltage very stable. Okay, I'm going to turn this off and jump back to our PowerPoint here. And in this first section, we just looked at Zeners as a regulating device, and we have other diodes we're going to look at in this section, but this will conclude part A of Special Diodes.